In this next lesson about torque, we're going to find the net torque that acts on an object. So when we have multiple torques, we typically will make the counterclockwise torque positive and the clockwise torque negative. So in this sample problem, we want to calculate the applied torque on a disk from three different forces. And you can see they're each acting with a different magnitude of force, and they could also be at a different lever arm. So on a disk, the lever arm is going to be effectively the radius of the circle that it's acting through. So the distance from the center out to where the force is applied. Notice it's in centimeters, so we'll have to be sure that we convert to the correct units. So, which ones are counterclockwise torque? So, if we imagine that we're holding a pencil at the center and pushing in the same direction that the 28 Newton force is pushing, you can see that this is going to be a counterclockwise torque. So the 18 Newton force, if we do the same thing, hold a pencil as though it's at the center and push the bottom of it to the left, you can see this is going to be a clockwise torque. And if we do that to the 35 Newton force, you can see that's also going to be a clockwise torque. So to figure out the net torque that acts on an object, we are going to find all of the counterclockwise torques and then subtract all of the clockwise torques. So our counterclockwise torque had a lever arm of 24 centimeters. So remember, torque is RF sine theta. So my lever arm in this case was 0.24 meters times a force of 28 newtons. You can see the angle between them is 90. So sine of 90 goes to 1. Minus, I have two clockwise torques. So the 18 Newton force is also acting at a lever arm of 0.24 meters times a force of 18 newtons times the sine of 90 minus the 35 Newton torque, but that lever arm is this inner circle. So that's going to be 0.12 meters times 35 newtons times the sine of 90. So if I type all of that into my calculator, I get negative 1.8 Newton meters of torque. So what does the negative mean? The negative means that it's clockwise. So this is the same as saying 1.8 Newton meters clockwise. That's going to be the net torque from all three of these forces. In the next example, I want to calculate the net torque about the axle of the wheel, but now it's telling me that friction will oppose the rotation, oppose the motion. And it tells me the magnitude of friction is 0.60 Newton meters. So, if my net torque from the three forces is clockwise, in order for friction to oppose it, friction has to act counterclockwise. So in this scenario, I have net torque equals, we'll call our torque from above the applied torque because it was from the 3 applied forces. Okay. And so we'll say the net torque, now that there's friction, is going to be T applied plus the torque from friction. And we don't have to worry about subtracting because the signs will take care of that. So our applied torque was negative 1.8 Newton meters of torque. Because our friction is opposing a clockwise motion, our friction is going to be positive 0.6 Newton meters because it will be counterclockwise. And so you can see that when we add those together, we get negative 1.2 Newton meters, or that means 1.2 Newton meters clockwise. Now we're going to look at applying torques to a uniform beam. So you can just imagine a straight rod. Now we need to pay attention to the pivot point. Okay, so we're looking for the net torque on this 2 meter long rod or uniform beam about point C. So point C is our axis of rotation. So if you take your pencil and you hold it at point C, and then you exert a force that matches the direction of each of these forces, it helps you to determine if it's a clockwise or a counterclockwise torque. So holding a pencil in the middle, just like point C, and then I push on the top of the pencil with my finger up and to the right, just as the 56 Newton force is, I can see that causes a rotation that is clockwise. I then come down to point C, which is the axis of rotation. And if I exert a force on point C up and to the left, notice it's not going to rotate. I'm exerting the force at the axis of rotation. So no torque will be exerted here. In terms of the equation, the lever arm is 0. So because the lever arm is 0, there's no torque as a result of the 65 Newton force. The 58 Newton force, again holding the pencil in the middle, pushing down and to the right in the same direction as the 52 Newton force, you can see that this is going to be a counterclockwise torque. So now I have to figure out the net torque based on these 3 forces. We already discussed the 65 Newton force won't be exerting a torque. So my net torque, remember this is RF sine theta. So it tells me it's a 2 meter long board. So for lever arm, I'm assuming it's 1 meter from top to C, 1 meter from C to the bottom. So my counterclockwise torque will be exerted at a lever arm of 1 meter times a force of 52 newtons times the sine of 58. And this is positive because it is counterclockwise. This is 65 Newton force does not exert a torque. So now I need to go to my clockwise torque, which is exerted by the 56 Newton force, also at a lever arm of 1 meter, times 56 newtons is the force, times the sine of 32. So I'm going to type that into my calculator and figure out what the net torque is. When I type that into my calculator, it tells me that I get a positive 14.42 Newton meter torque. And again, 14.42 Newton meters because it's positive. The net torque is in the counterclockwise direction. If we go down to part B, we have the exact same setup, the exact same forces. Okay, the difference though is now our axis of rotation is going to be about point P, so the bottom of this rod. So what effect does that have? You can see now that the lever arm on the 52 Newton force is 0. So the 52 Newton force is now no longer exerting a torque. So I'm going to take my pencil, I'm going to hold it vertically, and then I'm going to essentially mimic the two forces that are here. So first, holding my pencil at the bottom, I'm going to exert a force in the middle of the pencil, up and to the left in the direction of the 65 Newton force. I can see that that causes this to rotate counterclockwise. So this is going to be a counterclockwise torque. Now I'm going to test the 56 Newton force, holding it at the bottom, exerting a force at the top that's up and to the right. I can see this is going to exert a clockwise torque. So this will be a negative torque. This will be a positive torque. So now I have to plug it into my equation. So to figure out my net torque, I have to consider all of the different pieces. One other thing is going to be lever arm. So from the bottom, we know going up to the midpoint is 1 meter. And then we have another 1 meter to get to the top. So that means that the lever arm for the 56 Newton force is going to be the 2 meters. So net torque, we're going to start with the clockwise. So the clockwise torque exerted at point C is exerted at a lever arm of 1 meter. The force has a magnitude of 65 newtons, and it's exerted at an angle of 45 degrees. The clockwise torque I have to subtract. The clockwise torque is exerted at a distance or a lever arm of 2 meters from the axis of rotation point P. The force has a magnitude of 56 newtons, and the angle is 32 degrees. When I type that into my calculator, I get a value of negative 13.39 Newton meters. The negative indicates the clockwise direction, so this is saying 13.39 Newton meters clockwise. Okay, the next topic that we're going to talk about is going to be moment of inertia. So we know from Newton's second law, net force equals mass times acceleration, that the more mass there is, okay, the more an object is going to resist acceleration. So how does that translate in rotational motion? Well, instead of mass, we consider what's called moment of inertia, which is distribution of mass. In other words, how far the mass is from the axis of rotation. So what are some examples of this? So if you consider, an ice skater, when their arms are out, and they're spinning, the axis of rotation would be right here. So what they do when they're on the ice is they bring in their arms. And when they bring in their arms and they put their legs next to each other, you can see that the mass is now closer to the axis of rotation. So the effect is they brought the mass inward, closer to the axis. This decreases the moment of inertia. And what happens when the ice skater does this is, because of conservation of angular momentum, they'll start to spin faster. Same thing happens if you were to look at diving, right? When the diver jumps off the board, they'd be in a straight position. If they want to do a flip, they bring their body into a tuck and then rotate more quickly. And then when they're ready to enter the water, they straighten out again and the rotation slows. All of this happens because of moment of inertia, which is not just the amount of mass, but where the mass is. So you can see down here that moment of inertia we abbreviate with the letter I. And it's basically just the sum of mass times its distance from the axis of rotation squared. For however many masses that we have. So we're going to take a look at some examples of just calculating moment of inertia. If we go down to this one, we have a 5 kilogram mass and a 7 kilogram mass that are mounted 4 meters apart on a massless rod. Calculate the moment of inertia when the bar is rotated about an axis halfway between the weights. So you can see that's going to mean that this is now 2 meters. 5 kilogram mass is 2 meters from the axis. And the 7 kilogram mass is 2 meters from the axis. So how do I use this to calculate the moment of inertia? We can see it's the sum of the mass times the distance from the axis of rotation squared. So we're going to start with the 5 kilogram mass. And we can see that from the axis of rotation, which they show here, is this vertical line through the middle, times 2 meters squared. Plus, now we're going to look at the 7 kilogram mass. That's also 2 meters from the axis of rotation. And then we're going to plug it into our calculator to get a value. When we do that, we get 48 kilogram meters squared. So that is the unit for moment of inertia. And the moment of inertia is just how much an object is going to resist rotation. And the distribution of mass affects how much it will resist the rotation. In the next example, we're going to find the moment when the bar is rotated about an axis 0.5 meters away to the left of the 5 kilogram mass. So now this is my axis of rotation. So we haven't changed the objects, but we've changed the axis. Let's take a look at the effect that that has. So my moment is going to be the mass times the distance from axis of rotation squared. So I'll start with the 5 kilogram mass, and its distance is half a meter away. Now I'm going to go to the 7 kilogram mass, and you can see that its distance is 4 plus the 0.5, or 4.5 meters away. Now we'll type this into our calculator, and we get 143 kilogram meters squared. So you can see that the moment of inertia for the same object increased because of where the axis of rotation was. We didn't change any masses, we just changed where the axis of rotation was. Now, we have a new scenario. We don't have the picture, but we will make it here. So I have a 7 kilogram mass, and that's half a meter away, and because it's 50 centimeters, and we have a 5 kilogram mass, and the center of the rod is going to be the axis of rotation. So we're going to be rotating around this center line. So, same process for moment. The mass times its distance from the axis of rotation squared. So we have 5 kilograms times 0.5 meters squared plus 7 kilograms times 0.5 meters squared. And if I multiply all that out of my calculator, I get 3 kilogram meters squared. So the moment of inertia is equal to the sum of mr squared for each object. So if I think about the rule of ones and I compare part C to part A, you can see that the masses remain the same. However, the axis of rotation was quartered. So if I use the rule of ones, I know moment is going to depend on mr squared. Mass stayed the same. I'm going to put in a 1. I went from 2 meters away to 0.5 meters away, so that's going to be quartered. And that should be 1/16. And if I apply that 1/16 in part A, we have a moment of 48. So what is 1/16 of 48 kilogram meters squared? Well, it's 3 kilogram meters squared, which was our answer to part C. So you can see the rule of ones is able to be used as a predictive or to compare A to C. We also have some shortcut moment of inertia formulas based on what shape you're given, but also where the axis of rotation is. So we should highlight a few of these. First is the thin hoop. So you can see all the mass at the thin hoop is at the outside, which means all of the mass is a distance r away. And so the moment for the thin hoop is mr squared. All the mass is at a distance r. So it makes sense. It looks just like the generic equation. Another one we should highlight is the solid cylinder. The solid cylinder, you can see that the mass is not all at r, but the mass is distributed from the center all the way out. So the formula for the moment of inertia of a solid cylinder is 1/2 mr squared. So where m is the mass of the whole cylinder and r is its radius. And another one we should highlight is a uniform sphere. So think of, a ball, a bowling ball. So uniform meaning the mass is distributed uniformly from the center out throughout the sphere, and the moment for that is 2/5 mr squared. So these come up a lot, these three shapes in particular. We want to make sure that we know. So thin hoop is mr squared, solid cylinder is 1/2 mr squared, and a uniform sphere is 2/5 mr squared. Over here we have some examples of how we might use that. So in this problem, we're going to use the moment of inertia formulas to calculate the moment of a 4 kilogram pulley. So I know the mass is 4 kilograms, and I know it has a radius of 33 centimeters or 0.33 meters. And just to show you how these formulas will work, if I'm going to approximate the moment of the pulley, assuming it's a uniform cylinder or a solid cylinder, I'm going to say that the moment is equal to 1/2 mr squared. So if I plug that in, it's going to be 1/2 of 4 times 0.33 squared. Plug that into my calculator, and I get that my moment is 0.2178 kilogram meters squared. In part B, I'm asked to approximate the moment of the same pulley, but I'm going to model it as a thin hoop. Okay, now notice the axis of rotation is in the center and perpendicular to the plane of the hoop. So we'd be using the thin hoop radius r equation, mr squared, I equals mr squared. So this is going to be more because we're assuming all the mass is at the outside. So that's just going to be 4 times 0.33 squared. And it's going to end up being double, of course. So depending on the problem, you might have to use a different formula to model the mass distribution to figure out the moment of inertia. So that's a quick introduction to moment of inertia.